Hello, I am Somnath Dasgupta. I teach at Jamia Millia Islamia, New Delhi. Today in this module, we are going to talk about metamorphism under extreme thermal and baric conditions. Now, looking back when I was a student of metamorphic petrology in early 1970s, our textbooks specified that the upper limit of metamorphism temperature wise is about 750 degrees Celsius and pressure wise about 12 kilobars, which corresponds to the depth of the moho on an average. In 1980s, two dramatic things happened in metamorphic petrology. First of all, it was discovered from Antarctica that rocks can be metamorphosed to temperatures as high as 1000 degrees Celsius, even more. And secondly, it was discovered from the Italian Alps that crustal rocks can be taken down to mantle depths to as deep as 200 kilometers. Now, this changed the realm of metamorphism completely in 1980s, as a result of which two new concepts came into existence. One is ultra high temperature metamorphism, abbreviated as UHT, and ultra high pressure metamorphism, abbreviated as UHP. Now, I would refer to the figure 14.17, where you can see the metamorphic fasces plotted in PT space. Now, look at the bottom right hand corner. You will see a field of UHD metamorphism, and look at the upper right corner. You will find a field of UHP. So, this diagram will give you an overall idea about the pressure temperature domain of both UHD metamorphism and UHP metamorphism. Now, two questions that came into mind as soon as UHD and UHP metamorphism were discovered. First of all, in case of UHD metamorphism, what is the source of additional heat that raises the temperature of crustal rocks to 1000 degrees Celsius or more at depths of maximum 40 kilometers? Something is happening down there, otherwise you do not expect this much of temperature. And then in case of UHP metamorphism, the question is, how can you take the crustal rocks to mantle depths and then bring them up close to the surface, a process we call exhumation. So, both taking the crustal rocks to mantle depths and then bringing them back are both issues to which we did not have any answer at that time. Let us now look at the UHD metamorphism. Now, in figure 14.18, I have given you a global map showing the occurrences of UHD metamorphism as described so far. There are more than 60 of such occurrences. Now, look at the map of India. You will see several black dots. So, it means that a lot of cases of UHD metamorphism has been described from India as well. Now, traditionally, UHD metamorphism is defined as where metamorphic temperatures exceeds 900 degrees Celsius, and the pressure could be anything from 4 to 12 kilobars, corresponding to 15 to 40 kilometers of crustal depth. Most of the described UHD occurrences were metamorphosed at crustal pressures of 6 to 12 kilobars, mostly concentrating around 6 to 10 kilobars. Now, if you recall the discourse on granulite fascist metamorphism, you will remember that in granulite facies, pellitic rocks are partially molten. Now, if you keep the melt in place and still increase the temperature, what will happen? Simply the amount of melt will increase. But suppose by any process such as tectonism, you extract or take out the melt. If you take out the melt, then the temperature rises if additional heat is supplied in the restitic rocks, and that is how we get the so called magnesium aluminum granulites or high MgAl granulites characteristic of UHD metamorphosed pellitic rocks. In case of such rocks, there are certain specific mineral assemblages as well as mineral chemistry which are indicative of UHD metamorphism. Let us list them. Number 1, coexistence of sapphirine, this beautiful blue colored magnesium aluminum silicate with quartz. But you have to be careful that sapphirine does not contain lot of trivalent iron or trace elements or like beryllium, which increases the stability of sapphirine to down temperature. Second, the coexistence of spinel plus quartz. By spinel, I mean minerals belonging to the solid solution spinel hercinite MgL2O4 FeAl2O4. Coexistence of spinel with quartz is indicative of UHD metamorphism, provided spinel does not contain zinc, nickel, chromium and other similar elements. Thirdly, in many occurrences of UHD metamorphosed pellites, we get a lot of mesoparthites, that is intergrowth of plagioclase feldspar with alkali feldspar. Now, if we integrate the chemical composition of the two phases, we get ternary feldspars, that is a feldspar which was coexisting before exsolution took place to form the mesoparthite, and experimental data shows that such ternary feldspar can exist only at temperatures exceeding 900 degrees Celsius. So, mesoparthites are indicators of UHD metamorphism. Fourth, orthopyroxene traditionally contains high amount of aluminum in UHD metamorphosed pellites. It can go even as high as 8 to 13% of Al2O3. Now, if you recall that orthopyroxene strictly speaking does not contain Al2O3, because of Schermack substitution due to extreme temperatures of metamorphism, Al2O3 goes into the structure of orthopyroxene. So, highly aluminous orthopyroxene is characteristic of UHD metamorphism. Garnet can be pyrope rich in the sense that it can contain about 30 mole% of pyrope. Now, these are some of the characteristic features of UHD metamorphosed pellites. You can get corundum coexisting with sapphirine in silica deficient UHD metamorphosed pellites. You can get ausumelite in some UHD metamorphosed pellites. Ausumelite by itself is not indicator of UHD metamorphism, but if it coexists with sapphirine, you have a good case of UHD metamorphism. Now, these are the main characteristic features of UHD metamorphosed pellites. Now, these pellitic rocks show a number of important and interesting textural features which can be used to decipher the petrogenetic history, such as the pressure temperature path of evolution. For example, characteristic feature is the presence of coronitic textures. I document two such coronitic textures, strictly speaking double coronitic textures in figure 14.20, where sapphire and quartz are separated by double corona of orthopyroxene and sillimanite, indicative of the reaction sapphire plus quartz is equal to orthopyroxene plus sillimanite. In 14.23, I document another double corona texture where spinel and quartz are separated by double corona of garnet and sillimanite, indicative of the reaction spinel quartz giving garnet plus sillimanite. There is another kind of texture which is indicative of exsolutions of different kinds. As I said, orthopyroxene contains very high aluminum, titanium and other elements due to UHD conditions. When such orthopyroxenes cool, we get exsolution lamellae of sapphire, spinel, ilmenite and even garnet in orthopyroxene. These textures are shown in figures 14.21a and 21b. Then UHD metamorphosed palites also contain significant amount of opaque oxides, which contain very interesting exsolution intergrowths. These are documented in figure 14.22a and b, where iron, titanium, aluminum bearing spinels formed at high temperature absorbed several phases like ilmenite, magnetite, corundum. These textures are documented in figures 14.22. Now, let us look at the calcilicate rocks. As calcilicate rocks under UHD conditions contain the diagnostic mineral assemblage of scapolite plus olastonite plus minus plagioclase. Now, there are three reactions which are not affected by fluid composition in calcilicate rocks occurring under high temperature conditions are given in the figure 14.24, and these reactions are scapolite to plagioclase plus calcite, olastonite plus plagioclase to garnet plus quartz, and scapolite plus olastonite giving garnet, calcite, quartz. And these reactions are plotted in PT space in figure 14.24, and you can see that the field of scapolite plus olastonite plus minus plagioclase on the extreme right upper of the diagram is diagnostic of UHD metamorphism exceeding 900 degrees Celsius. Then you can also plot these some of the other reactions which are fluid dependent in TXCO2 space, which I have done in figure 14.25, and you can easily see the diagnostic mineral assemblages which are found at temperatures exceeding 900 degrees Celsius. There is another rock, ironstone, which was originally a sedimentary rock, iron rich. If such a rock is metamorphosed to UHD conditions, you can get inverted pigeonite, which is again indicator of UHD metamorphism. I will not discuss much about mafic granulites and the assemblages developed during UHD conditions, simply because mafic granulites had an igneous parentage. So, they had an igneous high temperature history, and there is always a debate how to separate this original high temperature history from the metamorphic high temperature history. So, let us not discuss much about the mafic granulites. Now, this is in summary the important textural features and mineral assemblages in metamorphosed UHD metamorphosed palites calcilicate rocks. Now, how do we estimate the temperature of metamorphism? Most of the common iron magnesium exchange thermometers, they reset during cooling and will not record the pre-existing ultra high temperature metamorphism. Some people are using trace element thermometry for this purpose, like zirconium in rutile, or titanium in zircon. Now, why so? Because trace elements are supposed to diffuse more slowly, and as a result they might record or preserve the UHD conditions even after cooling. In India, we have several occurrences of UHD metamorphosed rocks. Please refer again to figure 14.18. You will see many black dots. The most outstanding example will be the Eastern Ghats belt occurring along the east coast of India. These are regionally UHD metamorphosed belt, and then there are other occurrences in Kerala condylite belt, Madurai granulite belt, as well as some parts of central Indian tectonic zone. Now, the question that I raised at the beginning, that what is the source of the heat to cause UHD metamorphism? Lot of debate goes on, and we still await a final answer. Some people argue that in situations like modern back arc basins, which are locations of extension as well as high heat flow, where the original tectonic setting of UHD metamorphosed rocks. In any case, you have to replace the lithosphere by the hotter asthenosphere so that the temperature rises. This can happen due to lithospheric scale extension. This can happen due to mantle delamination, ridge subduction, as well as other processes like slab breakoff. Now, all these things have been suggested, and you will find references for all these work, but as I said, it is very difficult to come to a definitive conclusion. Now, let us go to the case of UHP metamorphism. Now, traditionally speaking, UHP metamorphism is defined at pressures exceeding 27 kilobars, which also corresponds to the pressure of quartz quartzite transformation. At this pressure, quartz transforms to quartzite, and the temperature should be more than 600 degrees Celsius. Refer to the figure in 14.17, where you will refresh your memory with the locations of the UHP metamorphism in PT space. At pressures higher than 27 kilobars, considerably higher so to say, carbon will be converted to diamond. And so, if metamorphism takes place at such great depths like 150 or 200 kilometers, you expect diamond to be present in the UHP metamorphosed rocks, provided there was carbon. Otherwise, of course, diamond cannot appear. Now, this is the, now there are several UHP metamorphosed rocks described from all over the world, and I will take you to the figure 14.27, where the geographical distribution of UHP metamorphosed rocks are visible. But you must see that most of these rocks occur close to either present day subduction zones or paleo subduction zones. Now, these UHP metamorphosed rocks are of pelitic type, quartzofelspathic type, even mafic granulite type. The diagnostic mineral assemblages in pelitic metamorphosed UHP metamorphosed rocks will again be the white schists, but this time instead of quartz you will get quartzite and you may get diamond. Now, quartzite and diamond have been discovered as only inclusion phases in garnet, zircon and other very resistant minerals. In figure 14.28, I have shown you some textures about occurrence of microdiamond and quartzite as inclusions in these minerals. Now, it is extremely difficult to get the quartzite and diamond today, because the rocks, when they came up to the surface, quartzite would have been converted to quartz and diamond would have been converted to carbon. But because of very slow reaction rate, we still get them in certain rare circumstances. In a mafic bulk composition, you can get gross spidite garnet or even majority garnet at extremely high pressure. You can get Ellenbergite inclusions in garnet, and of course you can get diamond, and if you had some free quartz, then quartzite might be stable. So this is the situation in ultra high pressure metamorphosed rocks. These textural features are shown in figure 14.28. One very interesting compositional aspect is that clinopyroxene may have substantial amount of extra silica which is absorbed out as quartz or even potash feldspar. So, high silica clinopyroxene is again an indicator of UHP metamorphism. So, the main question that comes to our mind is that how crustal rocks can be taken down to great depth in the mantle. Now, most of these UHP rocks are occurring in subduction zone settings, where subduction of cool oceanic lithosphere takes place. If the cool oceanic lithosphere subducts, then basalt is converted to eclogite, and eclogite being more dense than the surrounding mantle, the oceanic lithosphere is dragged down unless buoyancy takes over at great depth. Now, if a piece of continental crust is firmly attached to a descending cool oceanic lithosphere, then this can also travel to great mantle depths. This is the general model that we think of how to carry a continental crust to great mantle depths. Now, the continental crust must be detached at some stage so that it can come up to the surface. Now, this process can take place due to something like slab break off at great depth. When the slab breaks off, then the continental crust gets detached from the oceanic lithosphere, and because of the buoyancy and other tectonic processes, the continental crust then travels to somewhere near the surface. In figure 14.29, I have described 3 tectonic models which I have taken from the literature to explain how after detachment the continental crust can come back to close to the surface. The diagrams are self-explanatory, you can easily understand, but the 3 models are channel flow, tectonic wedging and wedge extrusion. These 3 are the available tectonic models by which from the great depth a continental crust can be brought up to shallow depths. Now, coming to the Indian occurrence, as expected, UHP rocks have been described only from the Himalayas in the Indian region as well as in the region falling in Pakistan as well. In the Indian part of the Himalayas, we have described UHP metamorphosed rocks from Ladakh, or more specifically So-Morari, and in So-Morari occurrence we have described both quartzite as well as microdiamond, indicating that the Indian continental crust also traveled to great depths of more than 150 kilometers. Now, geochronological study shows that this subduction which carried the continental crust to such great depths in the Himalayas occurred 52 to 55 million years before now. At that time, the initiation of the subduction took the continental crust to such great depths. This was followed by another orogenic pulse at around 27 to 30 million years before, when a Barrovian type of metamorphism was superimposed on the UHP metamorphosed rocks, and the rocks were carried to moderate depths back closer to the surface. Finally, in the Himalayas, we have the third phase of tectonic activity about 10 to 11 million years before, when doming started and the mountain chain formed. So, this is the story of the UHP metamorphosed rocks in our part of the Himalayas, which might be of interest to you. So, I now summarize the presentation to highlight that we have discussed the metamorphism under extreme thermal and baric conditions. Baric is nothing but pressure conditions, and we have discovered in 1980s UHT and UHP rocks, and I have told you about the features that you should look very carefully to find out about UHT and UHP rocks. And in particular, you can refer to the textural features. I have shown the different coronitic textures, and also in 14.24 there is a symplectite texture, which is a worm-like intergrowth of orthopyroxene and cordierite forming from garnet. This kind of textures give us lot of clues about the pressure temperature path of evolution of these rocks. So, these are important, these are very interesting. UHP metamorphism is obviously a rare tectonic phenomenon, and we are still searching for the real cause of UHP metamorphism. Similar is the case for UHT. So many models have been proposed, but I must say that a final answer is yet to be arrived at. Let us hope that in near future we will achieve these goals. Thank you very much.